Hello there, and welcome to Whispering Universes. Tonight we're diving deep into the vast blue world that covers most of our planet. The ocean stands infinite and eternal, its depths holding mysteries we are only beginning to understand. These waters cradle life in forms beyond imagination. They regulate our climate, shape our weather, and hold memories of Earth's ancient past. From the sunlit surface where dolphins play and phytoplankton bloom in countless trillions, to the crushing depths of ocean trenches where strange creatures glow in eternal darkness, these waters teem with wonders that challenge everything we think we know about life itself. Most of the time we see only the surface. We stand at the shore, watching waves roll in, feeling salt spray on our faces, listening to the endless rhythm of water meeting land, never imagining the vast three-dimensional universe that stretches beneath. Each wave that reaches the shore may have traveled thousands of kilometers, carrying with it the energy of distant storms and the chemical signatures of far-off currents. But the ocean is far from empty. It breathes with currents that span continents, moving more water than all the world's rivers combined. It pulses with life that glows in the darkness, creating bioluminescent displays that rival any aurora. It holds stories written in layers of sediment that record millions of years of Earth's history, and speaks in the songs of whales that travel across entire ocean basins. Science is only just beginning to map these depths, and what we discover grows more astonishing with each expedition. Submersibles descend into alien worlds where the pressure would crush us instantly, yet life thrives in abundance. Satellites peer down from space to track currents that influence weather patterns around the globe and monitor the health of marine ecosystems from hundreds of kilometers above. Deep-sea cameras capture footage of creatures so strange they seem to belong on another planet entirely. The ocean connects every continent, influences every climate, and touches every life on Earth. The water cycle that brings rain to distant mountains began with evaporation from ocean surfaces. The oxygen in every breath we take was likely produced by microscopic marine plants drifting in sunlit waters. The fish on our dinner plates were sustained by nutrients carried by ocean currents from depths where sunlight never penetrates. As always, if you enjoyed drifting off to science and wonder, be sure to like and subscribe or share a thought down below. But for now, let the sounds of the world above fade away. Feel yourself sinking gently into these peaceful depths, breathing slowly like the tide itself, and allow your mind to float among the endless blue mysteries that stretch from surface to seafloor, from Arctic ice to tropical coral reefs, across the vast watery realm that is our ocean planet. Let's begin.
When astronauts first looked back at Earth from space, they called it the blue marble, a perfect sphere of blue suspended in the cosmic darkness. This wasn't poetic license or an artistic interpretation. Water covers about 71% of our planet's surface, and nearly all of it is ocean. The Pacific Ocean alone is larger than all the continents combined, stretching from Asia to the Americas in an expanse so vast that ancient Polynesian navigators spent generations learning to cross it, reading the stars and the subtle patterns of waves to find tiny islands scattered across its immensity. These early navigators developed an intimate understanding of ocean patterns that modern science is only beginning to appreciate. They could read the color of water to determine depth, recognized the subtle differences in wave patterns that indicated the presence of distant islands, and navigate across thousands of kilometers of open ocean using only the stars, wind patterns, and their deep knowledge of ocean behavior. The ocean's total volume reaches over 13 billion cubic kilometers, a number so large it defies comprehension. If you could somehow collect all this water into a single sphere, it would be about 1,400 kilometers in diameter, large enough to contain several moons. To put this in perspective, if Earth were the size of a basketball, the ocean would be about as deep as a sheet of paper is thick. Yet within that thin blue layer exists the largest living space on our planet. The average depth of the ocean is about 3.7 kilometers, but this average conceals enormous variations. Vast abyssal plains stretch for thousands of kilometers at depths of 4 to 6 kilometers, while ocean trenches plunge to depths exceeding 11 kilometers. The continental shelves, where most ocean life concentrates, account for only about 8% of the ocean's area, but support a disproportionate amount of marine productivity.
Most of Earth's habitable volume lies beneath the waves, in depths where sunlight never penetrates, where pressure crushes with the weight of kilometers of water above, and where life has learned to make its own light. The ocean provides 99% of the living space on our planet. While we think of land as the domain of life, the truth is that most life exists in the sea, in forms we're only beginning to discover and understand. We divide this continuous body of water into 5 oceans: Pacific, Atlantic, Indian, Southern, and Arctic. But these are human constructs for our convenience. The ocean is one connected system, a global circulation of water that touches every continent and influences every climate. A drop of water in the Pacific will eventually find its way to the Atlantic, the Indian Ocean, and back again, carrying with it the chemical signatures of everywhere it has been. What happens in one part affects all others, making the ocean both vast and intimate, distant and essential to every breath we take. The boundaries between these named oceans are arbitrary lines drawn on maps. Water flows freely between them, carrying heat, nutrients, marine life, and human pollutants across these imaginary borders. The Southern Ocean surrounds Antarctica and connects the Pacific, Atlantic, and Indian Oceans. The Arctic Ocean, smallest and shallowest of the 5, plays an outsized role in global climate despite its size.
The sea is not just water, it's a solution containing nearly every element on the periodic table, a liquid library of Earth's chemistry dissolved and mixed over billions of years. This chemical complexity makes seawater one of the most complete natural solutions on our planet, containing traces of elements from the lightest hydrogen to the heaviest naturally occurring uranium. Magnesium is the second most abundant metal in seawater after sodium, and its presence affects many biological processes. Marine organisms have had to adapt to the high magnesium content of seawater, developing different biochemistry than their freshwater and terrestrial relatives. Some marine bacteria can only survive in the presence of high magnesium concentrations, making them obligate marine organisms. Potassium, sulfate, bromide, and dozens of other elements drift in solution, creating a chemical soup that mirrors the composition of life itself. The similarity between seawater and the fluid inside our cells is striking. Both contain similar ratios of sodium, potassium, and other ions, though in different concentrations. Some scientists think this resemblance isn't coincidental.
that life first emerged in these mineral-rich waters billions of years ago, and our blood chemistry still echoes the ancient sea. The ocean contains about 50 million billion tons of dissolved salt. If all this salt could be extracted and spread evenly across the land surface of Earth, it would create a layer about 150 meters thick. The salt content of the ocean has remained relatively stable for millions of years, with salt being added by weathering and volcanic activity, and removed by the formation of salt deposits and biological processes. Trace elements in seawater often limit biological productivity, despite being present in tiny concentrations. Iron, for example, is essential for photosynthesis, but is so scarce in many parts of the ocean that it limits phytoplankton growth. Adding iron to these areas can trigger massive blooms of marine life, demonstrating how even trace amounts of certain elements can control entire ecosystems. The ocean acts as Earth's largest reservoir of dissolved carbon dioxide, holding about 50 times more carbon than the atmosphere. This makes it both a buffer against climate change and a victim of it. As we pump more carbon dioxide into the atmosphere, the ocean absorbs much of it, helping to slow atmospheric warming, but at a cost. The dissolved carbon dioxide makes seawater more acidic, threatening creatures that build shells and skeletons from calcium carbonate. Every drop of seawater tells the story of our planet's chemistry, a liquid library of elements spanning geological time. The chemical composition of seawater reflects the balance between input from weathering, volcanism, and atmospheric deposition, and output through biological processes, sediment formation, and hydrothermal circulation. Despite covering most of our planet, the ocean remains largely unknown territory, more alien and inaccessible than the surface of Mars. We have better maps of the surface of Mars, Venus, and the Moon than of our own ocean floor. Less than 20% of the ocean has been mapped in detail, and only about 5% has been directly observed by humans. The deep sea is Earth's final frontier, closer to us than space, yet far more challenging to explore. The statistics are humbling. We've sent 12 people to walk on the Moon, but only 3 people have ever descended to the deepest part of our ocean, the Challenger Deep in the Mariana Trench. More people have been to space than have visited the deepest parts of our own planet. The technology required to explore these depths is more challenging than space travel in many ways. While space is empty, the deep ocean is full of crushing pressure that increases relentlessly with every meter of descent. At the average ocean depth of 3.7 kilometers, the pressure is about 370 times greater than at sea level. At the deepest point, Challenger Deep, at nearly 11 kilometers, the pressure exceeds 1,000 times atmospheric pressure, equivalent to having 50 jumbo jets stacked on top of every square meter. This pressure would instantly crush any ordinary vessel and requires specialized materials and engineering to survive. The technology for deep-sea exploration has advanced dramatically in recent decades, but it remains expensive and challenging. Modern deep-sea submersibles are marvels of engineering, built like small spacecraft with thick titanium hulls and life support systems that can sustain crews for hours in the abyss. Remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, have extended our reach into the deep ocean without risking human lives. Most of what we know about deep ocean life comes from brief glimpses, samples brought up in nets that may have traveled thousands of meters through different environments. Images captured by remote vehicles during short dives, or the occasional deep-sea creature that finds its way to shallow water or washes up on beaches. Each expedition to the deep ocean reveals new species, new ecosystems, new ways that life can adapt to conditions that seem impossible for anything to survive. Scientists estimate that between 500,000 and 2 million species live in the deep ocean, most of them unknown to science. Every deep-sea expedition discovers new species, sometimes dozens or hundreds in a single dive. A recent expedition to the Clarion-Clipperton Zone in the Pacific discovered over 30 new species in just a few weeks of exploration. These creatures have evolved in isolation for millions of years, developing bizarre adaptations to life in eternal darkness, crushing pressure, and near-freezing temperatures. Many deep-sea species are found only in specific locations, on particular seamounts, around specific hydrothermal vents, or in certain deep-sea basins. This high level of endemism means that entire species could be lost before they're even discovered, especially as human activities like deep-sea mining and fishing expand into previously unexplored areas. The deep ocean holds keys to understanding life's limits and possibilities. Extremophile organisms from the deep sea are being studied for potential applications in medicine, biotechnology, and astrobiology. The conditions in the deep ocean, high pressure, low temperature, chemical extremes, may be similar to those on other worlds, making deep-sea life a model for potential extraterrestrial organisms. Recent technological advances are accelerating deep-sea exploration. Autonomous underwater vehicles can now dive to the deepest parts of the ocean and map large areas without human intervention. Improved cameras and sensors provide unprecedented views of deep-sea life. Environmental DNA sampling can detect the presence of species without actually capturing them, providing new insights into deep-sea biodiversity. Yet, despite these advances, the ocean remains largely unexplored. Vast areas of the sea floor have never been visited by humans or even photographed. The deep ocean continues to yield surprises, new species, new ecosystems, new geological features with each expedition. The more we explore, the more we realize how little we know about our own planet's largest habitat. The ocean never rests. Even in the deepest trenches, water moves in currents that span the globe, driven by differences in temperature, salinity, and the rotation of our planet. These currents form a global circulation system more complex than Earth's atmosphere, moving billions of tons of water and heat around the planet every day in patterns that have persisted for millions of years. The Gulf Stream alone carries more water than all the world's rivers combined, about 30 million cubic meters per second at its peak flow. This massive current moves warm tropical water northward along the Atlantic coast of North America before crossing the Atlantic to warm northern Europe. The river of warm water is so large and powerful that it influences weather patterns across an entire continent, keeping cities like London and Paris surprisingly warm for their latitude. To put the Gulf Stream's scale in perspective, it carries about 150 times more water than the Amazon River, the world's largest river by volume. The current is typically about 100 kilometers wide and extends to depths of over 1,000 meters. As it flows northward, it carries not just water, but enormous amounts of heat, equivalent to the output of 1 million nuclear power plants. Without the Gulf Stream and its extension, the North Atlantic Current, northwestern Europe would have a climate more like northern Canada, despite being at the same latitude as southern Canada. The current explains why palm trees can grow in southwestern Ireland, while polar bears roam the Hudson Bay in Canada, which is actually farther south than much of Europe. Deep ocean currents form what scientists call the global conveyor belt, a circulation system that takes about 1,000 years to complete one cycle. This thermohaline circulation is driven by differences in water density caused by temperature and salinity variations. Cold, dense water sinks near the poles and flows along the ocean floor toward the equator, carrying oxygen to the deep sea and nutrients accumulated from decomposing organic matter. Meanwhile, warm surface water moves toward the poles to replace it, creating a circulation pattern that distributes heat around the planet and moderates climate. The sinking of cold, dense water in the North Atlantic and around Antarctica drives this global circulation. In the North Atlantic, water becomes dense enough to sink when it's cooled by Arctic air and made saltier by sea ice formation. This dense water, called North Atlantic deep water, flows southward along the ocean floor, eventually reaching the Southern Ocean, where it mixes with water from other ocean basins. Around Antarctica, the formation of sea ice creates some of the densest water in the ocean. When seawater freezes, it excludes salt, making the remaining liquid water saltier and denser. This Antarctic bottom water sinks and flows northward into all the world's ocean basins, carrying cold, oxygen-rich water to the deepest parts of the ocean. The Antarctic Circumpolar Current is the largest current system on Earth, flowing continuously around Antarctica and connecting all the world's major oceans. This current transports more water than all other ocean currents combined, about 600 times the flow of the Amazon River. Because it flows all the way around Antarctica without being blocked by continents, it helps isolate Antarctica from warmer waters to the north, maintaining the continent's ice sheets and influencing global climate. Ocean currents transport more than just water and heat. They carry nutrients from deep waters to the surface, supporting marine ecosystems around the world. They distribute marine life, carrying larvae and adult organisms across vast distances. They also carry human pollutants, spreading contamination far from its source and demonstrating how connected the ocean system really is.
Climate scientists worry that melting ice could disrupt this circulation by adding fresh water to polar regions, making surface water less dense and less likely to sink. Paleoclimate records show that this circulation has shut down or changed dramatically in the past, triggering rapid climate changes that affected the entire planet. If the global conveyor belt were to slow down or stop, it could lead to cooling in some regions and warming in others, with potentially catastrophic effects on weather patterns, agriculture, and human societies around the world. The precision and power of ocean currents have been recognized by humans for centuries. Polynesian navigators used their knowledge of currents to island hop across the Pacific. European explorers like Christopher Columbus took advantage of trade winds and currents to cross the Atlantic. Modern shipping still uses current patterns to reduce fuel consumption and travel time. Every second breath you take comes from the ocean, yet this fundamental connection between marine life and human survival remains largely invisible and unappreciated. While we often credit forests with producing oxygen and describe them as the lungs of the earth, marine plants and algae actually generate more than half of the oxygen in our atmosphere.
Single-celled organisms called phytoplankton, invisible to the naked eye, but numbering in the trillions, perform photosynthesis on a scale that dwarfs all terrestrial plant life combined. These microscopic organisms drift near the ocean surface, using sunlight to convert carbon dioxide and water into organic compounds and oxygen, just like plants on land. Though each individual phytoplankton cell is smaller than the width of a human hair, their collective impact shapes our planet's atmosphere. A single drop of seawater can contain thousands of these microscopic plants, each one a tiny factory producing the oxygen that sustains life on Earth. During spring blooms, satellite images show vast areas of ocean turning green as phytoplankton populations explode, triggered by increasing sunlight and nutrient availability. These blooms can cover hundreds of thousands of square kilometers, visible from space as swirling patterns of green in the blue ocean. A single bloom can produce as much oxygen in a few weeks as a forest produces in an entire year. The numbers are staggering. Marine phytoplankton produce somewhere between 50 and 80% of the oxygen in our atmosphere, with different estimates depending on seasonal variations and measurement methods. Diatoms, one of the most important groups of marine phytoplankton, are responsible for about 20% of global oxygen production, despite being microscopic single-celled organisms with intricate glass-like shells. Prochlorococcus, possibly the most abundant photosynthetic organism on Earth, is so small that millions could fit in a teaspoon of seawater. Yet this tiny bacterium is responsible for a significant fraction of ocean photosynthesis, producing oxygen that eventually makes its way into the atmosphere. These organisms are so small they were only discovered in the 1980s, yet they may be among the most important organisms on our planet.
Phytoplankton also form the base of almost every marine food web. Tiny animals called zooplankton eat the phytoplankton. Small fish eat the zooplankton. Bigger fish eat the small fish, and so on up to whales and sharks. This creates a pyramid of life that supports all marine ecosystems, from coastal kelp forests to the open ocean. The seasonal cycle of phytoplankton growth follows patterns of sunlight and nutrients. In temperate regions, spring blooms occur when increasing daylight triggers photosynthesis in nutrients that have accumulated during winter. In tropical regions, phytoplankton production may be more constant but can be limited by the availability of nutrients like nitrogen and phosphorus. Different types of phytoplankton dominate in different ocean regions and seasons. Diatoms, with their glass-like silica shells, are particularly important in cold, nutrient-rich waters. Coccolithophores, which build calcium carbonate plates, can form massive blooms that turn large areas of ocean a milky white color visible from space. Dinoflagellates can be both photosynthetic and predatory, some species producing toxins that can cause harmful algal blooms. Without these microscopic ocean plants, our marine ecosystems would collapse, and our atmosphere would have far less oxygen. It's humbling to think that our survival depends on creatures so small that millions could fit in a single drop of seawater, yet their total biomass and productivity exceeds that of all terrestrial vegetation. The ocean doesn't just surround us, it sustains us with every breath. The oxygen molecules entering your lungs right now may have been produced by a diatom floating in the Pacific Ocean, a coccolithophore in the Atlantic Ocean, or a prochlorococcus cell in the Indian Ocean. These molecules have traveled through the ocean,
into the atmosphere and around the globe to reach you, demonstrating the intimate connection between marine ecosystems and human life. Climate change and ocean warming could affect this crucial oxygen production. As water temperatures rise, the ocean's ability to hold dissolved gases decreases, and the distribution of nutrients changes. Some regions may become more productive, while others become less so, potentially altering the global patterns of oxygen production that have sustained life for millions of years. When we think of habitats, we picture forests with their towering trees reaching toward the sky, grasslands stretching to the horizon under vast open skies, or coral reefs bursting with colorful life in tropical shallows. But the deep ocean, waters below 200 meters, where sunlight cannot penetrate, represents more than 95% of Earth's living space. This vast, three-dimensional realm contains more volume than all other habitats combined, yet it remains largely unexplored and poorly understood. The deep ocean begins where the last traces of sunlight fade away, typically around 200 meters depth in clear water, but sometimes much shallower in murky coastal waters or deeper in the exceptionally clear waters of tropical oceans. Below this twilight zone lies a world of eternal darkness, where temperatures hover just above freezing and pressure increases relentlessly with depth. Yet this seemingly hostile environment teems with life in forms both beautiful and bizarre. The twilight zone, or mesopelagic zone, extends from about 200 to 1,000 meters depth and represents one of the largest migrations on Earth. Every night, billions of animals rise from these depths to feed in surface waters, then descend again before dawn. This daily vertical migration may involve more biomass than any other migration on the planet, yet it remains largely invisible to human observation. In the deep ocean, life exists without photosynthesis. No plants can grow here, so food comes from above in the form of marine snow, a constant gentle drift of dead plankton, fecal pellets, discarded mucus houses, molted shells, and organic debris falling from surface waters. This process creates one of nature's most efficient recycling systems, as nutrients are passed from organism to organism as they sink through thousands of meters of water. The journey from surface to seafloor can take weeks or months, and much of the organic matter is consumed or broken down before it reaches the bottom. Only about 1% of the organic matter produced in surface waters actually reaches the deep sea floor, making the deep ocean a food-limited environment where many animals must go long periods between meals. This scarcity of food has shaped remarkable adaptations in deep-sea creatures. Many have evolved expandable stomachs that allow them to consume prey much larger than themselves when the opportunity arises. Others have reduced their metabolic rates to near hibernation levels, allowing them to survive months without eating. Some have evolved to feed on detritus and bacteria, making use of every available food source. Deep-sea creatures have evolved remarkable adaptations to life in this eternal darkness. Many create their own light through bioluminescence, using chemical reactions to produce glowing displays that serve as communication between mates, camouflage against predators looking up from below, or lures for prey. Scientists estimate that up to 90% of deep-sea animals can produce light, creating a living constellation in the ocean's depths. The deep seafloor itself hosts diverse communities adapted to life on the sediment surface or buried within it. Polychaete worms burrow through the mud, creating networks of tunnels that allow oxygen and nutrients to penetrate deeper into the sediment. Sea cucumbers crawl across the seafloor like underwater vacuum cleaners, processing sediment and extracting nutrients. Xenophytophores, giant single-celled organisms that can grow larger than dinner plates, create complex shell structures from sand grains and organic debris. Hydrothermal vents and cold seeps create oases of life in the deep ocean, powered by chemosynthesis rather than photosynthesis. These ecosystems support unique communities of animals that exist nowhere else on Earth, including giant tube worms, clams, and crabs that have evolved partnerships with chemosynthetic bacteria. The deep ocean also serves as a vast reservoir for marine biodiversity. Many deep-sea species are found only in specific locations or depth ranges, leading to high levels of endemism. Each seamount, deep-sea canyon, or hydrothermal vent field may harbor species found nowhere else on Earth. The three-dimensional nature of the deep ocean creates countless microhabitats at different depths, each with its own physical and chemical conditions. The water column itself is stratified, with distinct layers characterized by different temperatures, salinities, and nutrient concentrations. These layers create barriers and boundaries that can isolate populations and promote speciation. The deep ocean shows us that life can thrive in conditions that seem impossible, creating beauty and complexity in the planet's darkest spaces. Each cubic meter of deep-sea water contains its own ecosystem, a community of bacteria, archaea, tiny animals, and organic particles invisible to the naked eye but essential to the ocean's function. As human activities increasingly impact the deep ocean through fishing, mining, and pollution, understanding and protecting these vast ecosystems becomes increasingly important. The deep ocean may hold keys to understanding life's limits and possibilities, potential sources of new medicines and biotechnology, and crucial insights into how our planet's largest habitat functions and responds to environmental change. The deepest places on Earth lie not on land but beneath the ocean, in vast chasms that plunge deeper into our planet than the highest mountains reach into the sky. Ocean trenches are among the most extreme environments on Earth, yet they teem with life that has adapted to conditions that seem incompatible with complex organisms. Ocean trenches are formed where tectonic plates collide and one slides beneath another in a process called subduction. The Mariana Trench in the Pacific Ocean reaches depths of over 11 kilometers at its deepest point, known as Challenger Deep. To put this in perspective, if Mount Everest were placed in Challenger Deep, its peak would still be over 2 kilometers underwater, completely submerged beneath the crushing weight of the ocean above. These trenches are not just deep, they are dynamic, geologically active regions where Earth's crust is being recycled in real time. As oceanic plates slide beneath continental plates, they carry with them sediments, water, and even pieces of the seafloor that may have existed for millions of years. This subducted material is heated and compressed as it descends into Earth's interior, eventually melting, and sometimes returning to the surface through volcanic eruptions that may occur hundreds of kilometers away from the trench. The pressure at the bottom of these trenches is almost incomprehensible. At Challenger Deep, the pressure exceeds 1,000 times atmospheric pressure, equivalent to having about 50 jumbo jets stacked on top of every square meter, or the pressure you'd experience if you were buried under 11 kilometers of solid rock. This pressure is so intense that it affects the very structure of water itself, making it slightly denser and changing its physical properties. Yet life exists even in these crushing depths.
in forms that challenge our understanding of biological limits. The deepest fish ever recorded was found at a depth of over 8,000 meters in the Japan Trench, living in conditions that would instantly kill most surface organisms. These fish have evolved special proteins that maintain their cellular structure under extreme pressure, and their bones are thin and flexible to avoid being crushed. Strange creatures called xenophyrophores carpet the deepest sea floor, single-celled organisms that can grow larger than dinner plates. These giant amoebas build elaborate shells from sand grains, organic debris, and even pieces of other organisms, creating some of the largest single cells known to science. Their size is possible because they don't rely on diffusion alone to transport materials throughout their bodies. They have developed internal currents and specialized structures that function like primitive organs. Amphipods, related to beach fleas, thrive at depths where the pressure would instantly crush most surface life. These small crustaceans have evolved specialized biochemistry that allows their proteins and cell membranes to function normally under extreme pressure. Some species are found only in the deepest trenches, having evolved in isolation for millions of years. The deepest parts of ocean trenches are also among the most isolated environments on Earth. Each trench system may harbor unique species found nowhere else, having evolved in isolation for millions of years. The deepest life forms have been separated from surface ecosystems for so long that they represent entirely different evolutionary lineages. Ocean trenches are also windows into our planet's deep processes, showing us how Earth constantly remakes itself over geological time. Sediments and crustal rocks that may have spent millions of years on the ocean floor are dragged deep into Earth's interior through subduction. This process recycles old crust and creates new crust at mid-ocean ridges, maintaining the dynamic balance of our planet's surface. The water in ocean trenches is often surprisingly clear despite the crushing depths. The extreme pressure prevents the formation of bubbles and particles that might cloud the water, and the isolation from surface waters means that sediment and organic matter settle slowly. This clarity allows the few scientists who have descended to these depths to see farther than might be expected in such an alien environment. Studying life in ocean trenches provides insights into the limits of life on Earth and potentially on other worlds. The extreme conditions in trenches may be similar to those in subsurface oceans on moons like Europa and Enceladus, making trench organisms models for potential extraterrestrial life. The trenches are also conveyor belts of geology, carrying pieces of the surface down into the planet's depths and recycling them over millions of years. Understanding this process helps us understand how Earth maintains its dynamic surface and how the planet has evolved over geological time. Some of the ocean's most beautiful and complex structures are created not by geological processes, but by tiny animals, smaller than your fingernail, working together over thousands of years to build living cities that can be seen from space. Coral polyps, related to jellyfish and sea anemones, are the architects of these underwater metropolises, extracting calcium carbonate from seawater and depositing it grain by grain to build their own homes. Each coral polyp is essentially a simple animal, a hollow cylinder with a mouth surrounded by tentacles. But what makes corals remarkable is their partnership with single-celled algae called zooxanthellae. These algae live inside the coral's tissues, using sunlight to photosynthesize and provide up to 90% of the coral's nutritional needs. In exchange, the coral provides the algae with shelter, nutrients, and a perfect position near the water's surface where sunlight is abundant.
This partnership is so intimate that the algae and coral function almost as a single organism. The algae's photosynthesis produces oxygen and organic compounds that the coral uses for energy and growth. The coral's waste products provide nutrients that the algae need for photosynthesis. This symbiotic relationship allows corals to thrive in nutrient-poor tropical waters, creating oases of life in oceanic deserts. The clear blue tropical waters that look so pristine to human eyes are actually nutrient-poor environments where few organisms can survive without special adaptations. The coral-algae partnership allows reefs to be incredibly productive, creating their own nutrient cycles and supporting complex ecosystems in these otherwise barren waters. Building a reef is a slow, meticulous process that requires precise environmental conditions. Individual coral polyps secrete calcium carbonate to form their skeletons, and these skeletons accumulate over time to form the reef structure. The process is remarkably similar to construction with concrete. The coral polyps extract calcium and carbonate ions from seawater and precipitate them as solid calcium carbonate. The Great Barrier Reef, built by countless generations of these partnerships, stretches over 2,000 kilometers along the Australian coast and supports about 25% of all marine species. The reef is actually a collection of over 2,900 individual reefs and 900 islands, ranging from small coral patches to massive reef systems that extend for kilometers. Some parts of the Great Barrier Reef are over 500,000 years old, built by countless generations of coral polyps working grain by grain. The growth rate of coral reefs varies with species and environmental conditions, but most reefs grow only a few centimeters per year. Fast-growing staghorn corals might add 10 to 20 centimeters per year, while massive brain corals might grow only 1 to 2 centimeters annually. This slow growth means that large reef systems represent thousands or millions of years of continuous construction. Different coral species have evolved different growth forms and strategies. Some corals grow in massive dome-shaped colonies that can survive storms and predation. Others grow in delicate, branching forms that maximize surface area for photosynthesis but are more vulnerable to damage. Table corals create horizontal platforms that shade other organisms, while brain corals form convoluted surfaces that increase the area available for their symbiotic algae. Coral reefs are among Earth's most productive ecosystems, rivaling rainforests in their biodiversity per unit area. The complex three-dimensional structure of a reef creates countless microhabitats, from sunny, shallow areas perfect for photosynthesis to dark caves and crevices that provide shelter for nocturnal animals. Each reef supports an intricate food web that includes everything from microscopic plankton to large sharks. The reef ecosystem extends far beyond the corals themselves. Sponges filter enormous amounts of water, removing bacteria and organic particles. Sea fans and soft corals add to the reef's three-dimensional complexity. Algae and seagrasses provide additional primary production. Fish, crustaceans, mollusks, and countless other animals find food and shelter within the reef structure. Yet these biological marvels are extremely sensitive to environmental changes. Rising water temperatures cause corals to expel their algal partners in a stress response called bleaching, leaving behind white coral skeletons that may die if conditions don't improve quickly.
Ocean acidification makes it harder for corals to extract the carbonate ions they need to build their skeletons, potentially slowing reef growth or even causing existing structures to dissolve. Pollution from coastal development can smother corals with sediment or trigger harmful algal blooms that block sunlight. Overfishing can disrupt the delicate balance of reef ecosystems, allowing algae to overgrow corals or removing key species that help maintain reef health. Climate change is causing more frequent and severe bleaching events, threatening reefs around the world. Many reefs around the world are struggling to survive in our rapidly changing ocean. Some have been damaged beyond recovery, while others show remarkable resilience and ability to adapt to changing conditions. Understanding how reefs respond to environmental stress is crucial for protecting these biodiversity hotspots and the millions of people who depend on them for food, coastal protection, and economic benefits.
Sound travels through water about 4 times faster than through air, and it can travel much farther with less energy loss, creating an acoustic environment completely different from anything we experience on land. In the deep ocean, low-frequency sounds can travel thousands of kilometers without significant attenuation, turning the ocean into a vast acoustic highway where sounds from distant sources can be heard across entire ocean basins. The speed of sound in seawater varies with temperature, pressure, and salinity, creating complex patterns of sound transmission that marine animals have learned to exploit. In warm surface waters, sound travels faster than in cold deep waters. This creates acoustic layers where sounds can be channeled and focused, similar to how optical fibers guide light. One of the most important acoustic features of the ocean is the SOFR channel, Sound Fixing and Ranging Channel, a layer of water where temperature and pressure conditions combine to create a natural acoustic waveguide. In this channel, sounds can travel thousands of kilometers with minimal loss, allowing marine animals to communicate across vast distances. The SOFR channel typically occurs at depths of 1,000 to 2,000 meters, where the effects of increasing pressure and decreasing temperature balance to create a minimum in sound speed. Sounds produced in this channel are bent back toward the channel axis when they try to escape, keeping them trapped within the acoustic waveguide like light in an optical fiber. Marine animals have evolved to use this acoustic environment in remarkable ways. Whales communicate across entire ocean basins using low-frequency calls that can travel hundreds or thousands of kilometers through the SOFR channel. Blue whales, the largest animals ever known to have lived, produce calls so low-pitched that humans can't hear them without special equipment. These infrasonic calls, typically between 10 and 40 Hz, are perfectly tuned to the ocean's acoustic properties.
A blue whale's call can reach 188 decibels underwater, louder than a jet engine and among the loudest sounds produced by any animal. Yet these calls are precisely tuned to travel the maximum distance with the least energy expenditure. The whales seem to understand the ocean's acoustic properties intuitively, producing calls at frequencies that can circle the entire globe. Different whale species have evolved different acoustic strategies. Humpback whales produce complex songs that can last for hours, with structured themes that repeat and evolve over time. These songs can travel hundreds of kilometers, allowing whales to communicate across vast areas of ocean. Male humpbacks seem to share songs across populations, with new musical phrases spreading across the Pacific Ocean like underwater hit songs. Sperm whales use a different acoustic strategy, producing powerful clicks that can penetrate into the deep ocean and return as echoes.
These whales can echolocate on squid and other prey at distances of several kilometers, using the most powerful sonar system in the natural world. Their clicks can reach 230 decibels, loud enough to potentially stun or kill their prey. The ocean also produces its own sounds from non-biological sources. Earthquakes rumbling along the seafloor create acoustic waves that can be detected thousands of kilometers away. The magnitude and location of underwater earthquakes can be determined by analyzing the sound waves they produce, providing an early warning system for tsunami. Icebergs create a symphony of sounds as they drift through the ocean. They groan and crack as they melt, produce popping sounds as air bubbles trapped in ancient ice are released, and create rumbling sounds when they roll over or break apart. These iceberg sounds can be detected by underwater microphones, helping scientists track ice loss from polar regions. Underwater landslides, volcanic eruptions, and even breaking waves contribute to the ocean's acoustic environment. The sound of rain hitting the ocean surface can be detected by underwater microphones, and different types of precipitation create different acoustic signatures. However, the ocean's acoustic environment is increasingly threatened by human activities. Ship noise has increased dramatically over the past century, creating a constant background noise that can interfere with marine animals' ability to communicate and navigate. Military sonar, seismic surveys for oil exploration, and underwater construction activities add to the acoustic pollution. This anthropogenic noise can have serious effects on marine life. Whales may change their calling behavior or abandon important habitat areas to avoid noisy shipping lanes. Some species may be forced to call more loudly or more frequently to communicate over human noise. In extreme cases, loud sonar has been linked to whale strandings and hearing damage. Understanding and protecting the ocean's acoustic environment is becoming increasingly important for marine conservation. The ocean's natural soundscape is as important to marine life as visual habitat is to terrestrial animals, and preserving it requires managing human activities that contribute to underwater noise pollution.
In the deep ocean, where sunlight never penetrates, many creatures make their own light through a process called bioluminescence, transforming the eternal darkness into a living constellation of biological stars. This ability to produce light is far more common in marine environments than on land, with scientists estimating that up to 90% of deep-sea animals can create light through chemical reactions within their own bodies. The chemistry behind bioluminescence involves a compound called luciferin reacting with an enzyme called luciferase in the presence of oxygen. This reaction produces light with remarkable efficiency. Nearly 100% of the energy is converted to light, with almost no heat produced. By comparison, an incandescent light bulb converts only about 5% of its energy to light, wasting the rest as heat. This efficiency is crucial for deep-sea organisms that must conserve energy in their food-limited environment. Different species use variations of this basic biochemical reaction to produce different colors and intensities of light. Most marine bioluminescence appears blue or blue-green, colors that travel farthest through seawater. However, some deep-sea creatures produce red light, which is invisible to most other deep-sea animals and may serve as a private spotlight for illuminating prey without alerting them to danger. These biological lights serve many purposes in the dark depths. Some animals use bioluminescence to communicate with potential mates, flashing specific patterns like underwater Morse code that can be recognized by members of their own species.
Deep-sea jellyfish create flowing displays of light that ripple through their translucent bodies, while some fish have light organs arranged in patterns unique to their species, allowing them to recognize potential mates in the darkness. The vampire squid, despite its ominous name, uses bioluminescence for defense rather than predation. When threatened, it can eject clouds of glowing mucus that confuse predators while it escapes. The squid can also turn itself inside out and cover its body with hundreds of bioluminescent photophores, creating a spectacular light show that startles potential threats. Many deep-sea animals use bioluminescence as camouflage in a strategy called counter-illumination. By producing light on their undersides that matches the faint glow filtering down from above, they can eliminate their silhouettes and become invisible to predators looking up from below. This biological stealth technology requires precise control of light intensity and color to match the changing conditions above. Deep-sea anglerfish have perhaps evolved the most ingenious use of bioluminescence. These fish dangle glowing lures to attract prey in the food-scarce deep ocean. The lure is actually a modified fin ray that extends from the fish's head like a fishing rod, complete with a glowing bait at the tip. Different species have evolved different lure shapes and light patterns, each designed to attract specific types of prey. Some bacteria, algae, and larger animals have evolved bioluminescent partnerships where bacteria living in specialized organs provide light for their hosts in exchange for nutrients and shelter. The Hawaiian bobtail squid uses bioluminescent bacteria to eliminate its shadow when hunting at night, making it invisible to prey looking up from below. The squid carefully controls the intensity of the bacterial light to match moonlight and starlight filtering down through the water. Certain deep-sea fish have evolved light organs that function like biological flashlights, allowing them to illuminate their prey before striking. These fish can control their bioluminescence precisely, turning it on and off at will, or adjusting its intensity depending on the situation. Some species have multiple light organs that can be controlled independently, creating complex lighting patterns. The lanternfish, one of the most abundant vertebrates on Earth, uses bioluminescence for both communication and camouflage. These small fish migrate vertically through the water column each night, following their zooplankton prey to surface waters. Their distinctive patterns of light organs allow them to recognize members of their own species during these massive migrations. Bioluminescence in the deep ocean creates one of nature's most spectacular displays, though few humans ever witness it directly. Submersible pilots and passengers describe the deep ocean as looking like a living galaxy, with countless points of light appearing and disappearing as animals communicate, hunt, and defend themselves in the darkness. Research into marine bioluminescence has led to important scientific and medical applications. The green fluorescent protein, originally discovered in jellyfish, is now used as a molecular marker in biological research, allowing scientists to track cellular processes and gene expression. Luciferase enzymes are used in medical diagnostics and environmental monitoring. In the deep ocean, bioluminescence transforms the darkness into a world of living light, where every flash, glow, and sparkle tells a story of survival, communication, or deception in Earth's largest habitat. This biological light show continues every night in the depths, a hidden symphony of light in the planet's darkest places.
Twice each day, the ocean rises and falls in response to gravitational forces from the moon and sun, creating one of the most predictable and powerful phenomena on Earth.
These tides represent the movement of trillions of tons of water in a rhythm that has continued for billions of years. Yet they can be predicted with extraordinary accuracy hundreds of years into the future. The precision of tidal predictions rivals that of celestial mechanics, and for good reason. Tides are a direct result of gravitational interactions between Earth, Moon, and Sun. The Moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the Moon. A corresponding bulge forms on the opposite side of Earth due to the centrifugal force of the Earth-Moon system. As Earth rotates beneath these bulges, any given location experiences 2 high tides and 2 low tides each day. The Sun also influences tides, though its effect is smaller than the Moon's, despite the Sun's much greater mass. This is because tidal forces depend on the difference in gravitational pull across Earth's diameter, and the Moon's closer proximity makes its tidal influence about twice as strong as the Sun's. When the Sun and Moon align during new and full moons, their gravitational effects combine to create especially high spring tides. When they are at right angles during quarter moons, they partially cancel each other out, creating lower neap tides. Tidal forces don't just move water up and down coastlines, they create powerful currents that flow through straits and around islands, sometimes reaching speeds of over 20 kilometers per hour. These tidal currents can be so strong that they create underwater waterfalls and rapids, carving channels in the seafloor and stirring nutrients from deep waters to the surface.
In some places, like the Bay of Fundy in eastern Canada, the shape of the coastline and seafloor amplifies tidal ranges to extraordinary levels. The Bay of Fundy experiences tidal ranges exceeding 15 meters, the height of a 5-story building. At low tide, vast mudflats stretch for kilometers, exposing an underwater world of marine life adapted to this twice-daily transformation. 6 hours later, the same area is covered by deep water, creating a dramatic change that shapes entire ecosystems. The Old Sow Whirlpool between Maine and New Brunswick demonstrates the power of tidal currents. As billions of gallons of water rush through narrow passages between islands, they create whirlpools and standing waves that can be dangerous to small boats. The turbulence mixes different water masses and brings nutrients to the surface, creating feeding areas for seabirds and marine mammals. Tidal bores are among the most dramatic tidal phenomena, where the incoming tide forms a wave that travels up rivers, sometimes for hundreds of kilometers inland. The Qiantang River in China produces tidal bores that can reach heights of 9 meters and travel at speeds of 40 kilometers per hour, creating a wall of water that surfers and spectators gather to witness. The bore can be heard from kilometers away as it approaches, producing a sound like distant thunder. The Amazon River experiences one of the world's most powerful tidal bores, called the Pororoca. This bore can travel 800 kilometers upstream, reversing the flow of the river and creating waves up to 4 meters high. The bore brings salt water and marine life far inland, temporarily transforming freshwater ecosystems into marine environments. The energy in tidal movements is enormous. Billions of tons of water moving twice daily with clockwork precision. A single tide can move more water than all the world's rivers combined. This energy is gradually dissipated through friction with the seafloor and coastlines, causing Earth's rotation to slow by about 2 milliseconds per century. This tidal friction also causes the Moon to slowly spiral away from Earth at a rate of about 3.8 centimeters per year. In the far future, billions of years from now, tidal forces will eventually synchronize Earth's rotation with the Moon's orbit, causing one side of our planet to always face the Moon, just as one side of the Moon always faces Earth.
At that point, there will be no more tides, and the moon will appear stationary in the sky. Engineers are beginning to harness tidal energy as a renewable power source. Tidal power plants use the predictable movement of water during tidal cycles to generate electricity, offering a reliable alternative to wind and solar power that doesn't depend on weather conditions. The Reims tidal power station in France has been generating electricity from tides since 1966, demonstrating the long-term viability of this technology. The total potential energy in tides worldwide could supply a significant fraction of human electricity needs. Unlike wind and solar power, tidal energy is completely predictable. We know exactly when and how strong tides will be centuries into the future. This predictability makes tidal power an attractive complement to other renewable energy sources. Tidal forces also affect the Earth itself, causing the land to rise and fall by as much as 30 centimeters twice daily. These Earth tides are much smaller than ocean tides, but can be measured with sensitive instruments. They affect the precision timing required for GPS satellites and must be accounted for in precise surveying and navigation. The water in today's oceans is ancient beyond human comprehension, containing molecules that have been cycling through Earth's systems for billions of years. Through the water cycle, ocean water evaporates, rises into the atmosphere, falls as rain and snow, flows through rivers and groundwater systems, and returns to the sea in an endless circulation that has continued since Earth first developed the oceans over 4 billion years ago. This recycling process means that ocean water contains the history of our planet dissolved in solution. Every water molecule has a story spanning geological time, having participated in countless cycles through atmosphere, land, and sea. The water molecules in your body have likely traveled through clouds over ancient continents, fallen as rain in prehistoric forests, flowed through rivers that no longer exist, and been incorporated into the bodies of countless organisms throughout Earth's history. Some water molecules have been cycling through the ocean system for over 3 billion years, since the first stable oceans formed on our planet. These ancient molecules have witnessed the entire history of life on Earth, the emergence of the first single-celled organisms that learned to use sunlight for energy, the evolution of photosynthesis that began to fill the atmosphere with oxygen, the rise and fall of countless species, and the gradual transformation of our planet's atmosphere and climate. The chemical signatures preserved in seawater tell stories of past environments. Dissolved minerals carry evidence of ancient volcanic eruptions that spewed gases and particles into the atmosphere millions of years ago. Isotope ratios in seawater reflect past climate changes, ice ages, and periods of global warming that occurred long before humans existed. The very salt content of the ocean preserves information about the weathering of ancient mountains and the chemical evolution of our planet's surface. The ocean acts as Earth's chemical memory, preserving information about past climates in multiple ways. The shells of marine organisms that lived millions of years ago contain isotopic signatures that reveal ancient ocean temperatures and atmospheric carbon dioxide levels. Layers of sediment on the ocean floor preserve records of past volcanic eruptions, asteroid impacts, and changes in ocean circulation patterns. Ice cores from glaciers and sediment cores from the deep ocean allow scientists to reconstruct Earth's climate history going back millions of years. These archives show how our planet's climate system has responded to past changes in atmospheric composition, solar radiation, and ocean circulation. They reveal that Earth's climate can change rapidly when pushed beyond certain thresholds, providing crucial insights for understanding current climate change. Different parts of the water cycle operate on vastly different timescales, creating a complex system of water storage and exchange. Water vapor in the atmosphere has an average residence time of about 9 days before condensing and falling as precipitation. Water in rivers may flow to the ocean within weeks or months. But water in deep ocean currents may not return to the surface for hundreds or thousands of years. Groundwater represents one of the slowest parts of the water cycle. Some groundwater aquifers contain water that fell as rain tens of thousands of years ago and has been slowly moving through underground rock formations ever since. This fossil water provides insights into past climate conditions and may contain dissolved minerals that tell stories of ancient geological processes.
Water trapped in ice sheets represents another slow component of the water cycle. Ice in the center of the Antarctic ice sheet may be over 800,000 years old, containing air bubbles that preserve samples of ancient atmospheres. As this ice eventually melts and returns to the ocean, it releases water that was locked away during past ice ages. The biological components of the water cycle add another layer of complexity. Water that evaporates from forest leaves has been filtered through plant tissues and may carry chemical signatures of biological processes. Water that flows through ecosystems picks up nutrients, organic compounds, and other materials that reflect the health and composition of those ecosystems. This ancient recycling system connects all life on Earth through currents of water, chemistry, and energy that span the globe. What happens in one part of the water cycle affects all others, just as what happens to the ocean affects all life on land. The Amazon rainforest depends on water that evaporated from the Atlantic Ocean. Arctic ice sheets contain water that fell as snow after evaporating from tropical seas. Human activities are now affecting this ancient cycle in unprecedented ways. We're changing the chemical composition of rainwater through air pollution, altering river flows through dams and diversions, and adding new chemical compounds to the water cycle through industrial activities. Understanding how human actions affect the global water cycle is crucial for managing water resources and predicting future environmental changes. We are all part of this ancient cycle, temporary custodians of water molecules that have journeyed through time since the birth of our planet's oceans. Every glass of water we drink contains molecules that may have been part of ancient seas, fallen as rain on dinosaurs, or been locked in ice for millennia. We are connected to all of Earth's history through the water that flows through our bodies and returns to the endless cycle that began when our planet first developed its blue marble appearance billions of years ago. Beneath the ocean lies the world's longest and most volcanically active mountain range, the Mid-Ocean Ridge System. This underwater mountain chain stretches over 65,000 kilometers around the globe, more than twice the circumference of Earth and 4 times longer than the Andes, Rockies, and Himalayas combined. If you could drain the oceans, you would see a landscape more rugged and dramatic than any mountain range on land, with towering peaks, deep valleys, active volcanoes, and vast plateaus stretching to every horizon. The mid-ocean ridges are where new ocean floor is born through a process called seafloor spreading that has been operating for over 200 million years. Magma rises from Earth's interior through cracks in the ridge axis, cooling and solidifying to form new seafloor at rates of a few centimeters per year.
This process is constantly creating new oceanic crust, while older crust is destroyed at ocean trenches, maintaining a dynamic balance in the ocean basins. The East Pacific Rise, part of the mid-ocean ridge system in the Pacific Ocean, spreads faster than any other ridge, creating new sea floor at rates up to 18 centimeters per year. The Mid-Atlantic Ridge spreads much more slowly, at about 2 to 3 centimeters per year, roughly the rate at which your fingernails grow. Despite these seemingly slow rates, over millions of years this process has created all of the ocean floor currently in existence. As new crust forms at the ridges, it carries a magnetic record of Earth's magnetic field reversals in the iron-bearing minerals that crystallize from the cooling magma. Over millions of years, Earth's magnetic field has reversed many times, and these reversals are recorded as stripes of alternating magnetic polarity on the seafloor. This discovery in the 1960s provided crucial evidence for the theory of plate tectonics and revolutionized our understanding of how Earth's outer shell moves and changes over geological time. The magnetic stripes on the seafloor create a natural tape recorder of Earth's magnetic history. By measuring the width of these stripes and their distance from the ridge axis, scientists can calculate how fast the seafloor has been spreading and determine when magnetic reversals occurred in the past. This magnetic record extends back over 180 million years and provides one of the most complete archives of Earth's magnetic field behavior. The mid-ocean ridges are not uniform structures, but include a diverse array of underwater landscapes. Fast-spreading ridges like the East Pacific Rise have broad, low-relief volcanic zones with extensive lava flows. Slow-spreading ridges, like the Mid-Atlantic Ridge, have deep rift valleys bounded by steep mountain walls, where the sea floor is being pulled apart faster than volcanic activity can fill the gap. Transform faults cut across the ridge system at regular intervals, creating fracture zones that can extend for thousands of kilometers across the ocean floor. These faults accommodate the different spreading rates and directions of adjacent ridge segments, creating some of the most tectonically active areas on Earth. The movement along these faults generates earthquakes and creates dramatic underwater cliffs and valleys. The ridge system hosts unique ecosystems centered around hydrothermal vents, underwater hot springs where superheated water, rich in dissolved minerals, erupts from the sea floor. These vents create oases of life in the deep ocean that depend on chemosynthesis rather than photosynthesis. The discovery of these ecosystems in the 1970s revolutionized our understanding of life's possibilities and showed that entire ecosystems could exist independently of solar energy. Different types of hydrothermal vents form at different ridge settings. Fast-spreading ridges tend to have low-temperature diffuse venting over broad areas, while slow-spreading ridges often have high-temperature black smoke events that build tall chimney structures. The chemistry of the vent fluids varies depending on the rocks they flow through and the temperatures they reach, creating different chemical environments that support different types of life. The ridge system also influences ocean circulation and climate on a global scale. The underwater topography channels deep-sea currents, creating pathways for cold water to flow from polar regions toward the equator. The heat from ridge volcanism warms deep ocean waters, affecting their density and circulation patterns. The chemical composition of ridge rocks affects the chemistry of seawater as it circulates through the hot volcanic rocks. Massive sulfide deposits form around hydrothermal vents where metal-rich fluids precipitate minerals as they cool in contact with seawater. These deposits contain valuable metals like copper, zinc, lead, gold, and silver, making them targets for potential deep-sea mining operations. However, extracting these deposits would destroy the unique ecosystems that depend on hydrothermal activity. The ridge system is constantly changing as new volcanic eruptions create fresh seafloor and tectonic forces shift the positions of ridge segments. Underwater volcanic eruptions at mid-ocean ridges are far more common than terrestrial eruptions, but are rarely observed because of their remote locations. Most of our knowledge about ridge volcanism comes from studying the volcanic rocks that form there and observing the aftermath of eruptions. Recent technological advances have allowed scientists to observe ridge volcanism in real time using networks of underwater seismometers and seafloor observatories. These instruments can detect the small earthquakes that often precede volcanic eruptions and monitor changes in water temperature and chemistry that indicate volcanic activity.
The mid-ocean ridge system represents one of the most dynamic and important geological features on our planet, constantly creating new seafloor and hosting unique ecosystems that challenge our understanding of life's limits. As we continue to explore these underwater mountain ranges, we discover new insights into how our planet works and how life can thrive in some of Earth's most extreme environments.
In the deep ocean, it's always snowing. This biological blizzard, called marine snow, consists of a constant gentle shower of organic material falling from surface waters toward the sea floor thousands of meters below. Unlike terrestrial snow, these snowflakes are made not of ice but of life itself. Dead plankton, fecal pellets, discarded mucus houses, molted shells, pieces of larger animals, and clumps of bacteria and algae stuck together with sticky organic compounds. The name marine snow comes from the appearance of this falling material when viewed through underwater cameras or from the portholes of submersibles. The organic particles drift slowly downward through the water column, like snowflakes in a gentle blizzard that never stops. Individual flakes can range from microscopic particles smaller than a grain of sand to aggregates several centimeters across that tumble slowly through the water like underwater leaves. The density and composition of marine snow varies dramatically depending on the productivity of surface waters above and the season. During spring phytoplankton blooms, the marine snow may be rich in fresh organic matter from recently dead algae. In areas with many grazing animals, fecal pellets may dominate the falling material. Near coastlines, terrestrial organic matter washed from rivers may contribute to the marine snow, while in the open ocean, it consists almost entirely of marine-derived material. As marine snow falls through the water column, it provides food for deep-sea creatures at every depth, creating a vertical food web that connects surface productivity to deep-sea ecosystems. Some animals specialize in catching these falling particles with elaborate filters or nets, spreading feeding appendages like underwater spider webs. Salps and other gelatinous animals filter vast amounts of water to capture marine snow. Deep-sea fish with large mouths and expandable stomachs wait for larger pieces of falling organic matter. The journey from surface to seafloor can take weeks or months, depending on the size and density of the particles and the depth of the water. During this long fall, much of the organic matter is consumed or broken down by bacteria and other microorganisms that colonize the particles as they sink. This bacterial activity transforms the chemical composition of marine snow as it falls, breaking down complex organic compounds and releasing nutrients. Only about 1% of the organic matter produced in surface waters actually reaches the deep sea floor intact, making the deep ocean a food-limited environment where many animals must go long periods between meals. This efficiency of recycling means that organic matter may be consumed and repackaged many times as it sinks through different depth zones. Marine snow plays a crucial role in the ocean's carbon cycle and global climate regulation. When organic matter sinks to the deep ocean, it carries carbon away from the atmosphere and stores it in the deep sea for hundreds or thousands of years. This biological pump helps regulate Earth's climate by removing carbon dioxide from the atmosphere and storing it in the deep ocean. The sinking of marine snow is one of the most important mechanisms for transporting carbon from the surface to the deep ocean. Phytoplankton near the surface remove carbon dioxide from seawater during photosynthesis, incorporating it into their cells. When these organisms die and become part of marine snow, they carry this carbon with them as they sink. If the carbon reaches the deep ocean, it may be stored there for centuries before returning to the surface through upwelling. Different types of marine organisms contribute different types of particles to marine snow. Diatoms, single-celled algae with glass-like shells, create dense particles that sink quickly. Coccolithophores, which build calcium carbonate plates, contribute both organic carbon and calcium carbonate to marine snow. The shells and plates from these organisms can protect organic matter from bacterial decomposition, helping more carbon reach the deep ocean. Fecal pellets from zooplankton represent a particularly important component of marine snow. These pellets are often surrounded by membranes that protect the organic matter inside from bacterial attack, allowing nutrients and carbon to be transported rapidly to depth. Large zooplankton can package organic matter into fecal pellets that sink much faster than individual phytoplankton cells. The aggregation of small particles into larger marine snow flakes is facilitated by sticky organic compounds produced by marine organisms. Transparent exopolymer particles, TEP, produced by phytoplankton and bacteria, act like underwater glue, binding smaller particles together into larger aggregations that sink faster. This aggregation process is crucial for the efficiency of the biological pump. Seasonal changes in surface productivity create seasonal variations in marine snow. In temperate regions, spring blooms produce pulses of marine snow that can be tracked as they sink through the water column. These pulse events can dramatically increase food availability in the deep ocean and trigger reproductive cycles in deep-sea organisms.
Human activities are affecting marine snow production and composition. Climate change is altering the timing and magnitude of surface blooms, potentially affecting the amount and timing of food delivery to the deep ocean. Ocean acidification may affect the ability of shell-building organisms to contribute to marine snow. Pollution can alter the chemical composition of marine snow and potentially make it toxic to deep-sea organisms. This underwater blizzard creates a connection between surface productivity and deep-sea ecosystems thousands of meters below, demonstrating how the ocean functions as an integrated system where changes in surface waters can affect life throughout the water column. The gentle fall of marine snow represents one of Earth's most important biological processes, sustaining deep-sea life and helping regulate global climate through the transport and storage of carbon in the deep ocean. The largest animals on Earth are also among the most vocal, producing some of the most powerful and far-traveling sounds in the animal kingdom. Blue whales,
the largest animals ever known to have lived, produce calls that can be heard across entire ocean basins, using the ocean's natural acoustic properties to communicate over distances that would be impossible in any other environment on Earth. A blue whale's call can reach 188 decibels underwater, louder than a jet engine, and among the loudest sounds produced by any animal. To put this in perspective, these calls are more powerful than most human-made sounds and can be detected by underwater listening devices thousands of kilometers away. Yet these powerful calls are precisely tuned to the ocean's acoustic properties, using frequencies between 10 and 40 Hz that can travel the farthest with the least energy loss. The low frequency of blue whale calls allows them to travel through the ocean's natural sound channels with minimal attenuation. In the SOFR channel, a layer of water where temperature and pressure conditions create an acoustic waveguide, these calls can circle the entire globe. A blue whale calling in the Pacific Ocean could theoretically be heard by another blue whale on the opposite side of the planet, though the calls would take hours to travel that distance. Different whale species have evolved distinct acoustic signatures that allow them to be identified by their calls alone. Blue whales in North Pacific basins produce calls that are distinctly different from those in the North Atlantic, and both are different from Antarctic blue whales.
Humpback whales produce some of the most complex songs in the animal kingdom, with structured themes that can last for hours. These songs include repeated phrases that follow predictable patterns, similar to human music. Male humpbacks seem to be the primary singers, and their songs change over time in fascinating ways. New song elements appear and spread through populations like musical fashions, sometimes traveling across entire ocean basins faster than the whales themselves migrate. The cultural transmission of humpback whale songs has been documented across the Pacific Ocean. New song elements that appear in Eastern Australia populations can be detected in Ecuadorian populations within a few years, apparently spreading westward across the Pacific through acoustic communication. This represents one of the fastest documented cases of cultural change in any animal species. Fin whales produce some of the most regular sounds in the ocean, rhythmic calls at precisely 20-second intervals that can be detected by seismometers on land. These calls are so regular and powerful that they were initially mistaken for sonar signals during the Cold War. The geometric precision of fin whale calling patterns suggests sophisticated neural mechanisms for timing that we don't yet understand. Sperm whales use a different acoustic strategy, producing powerful clicks that can penetrate deep into the ocean and return as echoes. These whales have evolved the most powerful sonar system in the natural world, capable of echolocating on squid and other prey at distances of several kilometers. Their clicks can reach 230 decibels, loud enough to potentially stun or disorient their prey. The complexity of sperm whale acoustic behavior extends beyond echolocation. They produce complex sequences of clicks called codas that appear to function as social signals. Different sperm whale populations have different coda repertoires, suggesting cultural dialects similar to those seen in human languages. Family groups may have signature codas that help individuals recognize their relatives in the vast ocean. Gray whales undertake one of the longest migrations of any mammal, traveling from Arctic feeding grounds to tropical breeding areas and back again.
Their low-frequency calls may help them navigate during these epic journeys, using acoustic landmarks like the sounds of breaking waves on distant shores or the echoes of their calls from underwater features. Right whales produce calls that travel hundreds of kilometers through coastal waters. These highly endangered whales use their calls to maintain contact with widely dispersed family members and to coordinate feeding activities. Unfortunately, ship noise in busy shipping lanes may interfere with right whale communication, potentially affecting their ability to find food and mates. Scientists are still discovering how whales use these long-distance calls. They may help coordinate feeding in areas rich with krill, allowing whales to share information about food sources across vast areas. Calls may help whales maintain contact with family members during long migrations or find mates in the enormous spaces of the open ocean. The ocean's acoustic environment has changed dramatically over the past century as ship traffic has increased exponentially. The low-frequency noise from ship engines overlaps with the frequency range used by many whale species, potentially interfering with their communication. This acoustic pollution may force whales to call more loudly, change their calling behavior, or abandon important habitat areas.
Military sonar and seismic surveys for oil exploration add to the acoustic pollution in the ocean. These activities can produce sounds loud enough to cause hearing damage in marine mammals and have been linked to whale strandings in some cases. Understanding and managing human impacts on the ocean's acoustic environment is becoming increasingly important for whale conservation. The study of whale acoustics has also provided insights into ocean physics and climate change. Whale calls can be used to monitor ocean temperature changes, as the speed of sound in seawater varies with temperature. Long-term recordings of whale calls have revealed changes in ocean acoustic properties that reflect global warming. The ocean's acoustic environment allows whales to live in social groups spread across thousands of kilometers, connected by songs that bridge the vast distances of the sea. These acoustic connections create social networks that span entire ocean basins, demonstrating how sound can unite marine communities across scales impossible in any terrestrial environment. The ocean's surface is dominated by 5 massive circular current systems called gyres that operate like giant clockwork mechanisms, each covering millions of square kilometers and rotating with a precision that has remained stable for millions of years. These rotating systems, driven by persistent trade winds and Earth's rotation, move warm water toward the poles and cold water toward the equator in patterns that fundamentally shape global climate and marine ecosystems. The North Atlantic gyre includes the famous Gulf Stream, which carries warm tropical water northward along the eastern coast of North America before crossing the Atlantic as the North Atlantic Current to warm northern Europe. This current system transports about 30 million cubic meters of water per second, roughly 150 times the flow of all the world's rivers combined. The heat carried by this gyre is equivalent to the output of 1 million nuclear power plants, demonstrating the enormous energy involved in ocean circulation. In the Pacific, the North Pacific Gyre covers an area larger than North America, slowly rotating clockwise over a period of about 6 years. A piece of floating debris entering this gyre might take decades to complete a full circuit, carried by currents that move at typical speeds of just a few centimeters per second. This seemingly slow motion actually involves the movement of vast amounts of water and has profound effects on climate and marine life distribution.
The gyres are driven by the interaction of surface winds and the Coriolis effect from Earth's rotation. Trade winds near the equator push water westward, while westerly winds at higher latitudes push water eastward. The Coriolis effect, caused by Earth's rotation, deflects moving water to the right in the northern hemisphere and to the left in the southern hemisphere, creating the circular motion of the gyres. The Antarctic circumpolar current is unique among ocean currents because it flows completely around Antarctica without being blocked by continents. This current system is the largest on Earth, transporting more water than all other ocean currents combined, about 600 times the flow of the Amazon River. The current connects all the world's major oceans and helps isolate Antarctica from warmer waters to the north, maintaining the continent's ice sheets and influencing global climate. The centers of ocean gyres are characterized by relatively calm conditions and downwelling, where surface waters sink to intermediate depths. This downwelling concentrates floating material, including both natural organic matter and human-made debris. The Sargasso Sea in the center of the North Atlantic Gyre is famous for its vast mats of floating sargassum seaweed, which create unique ecosystems in the open ocean. These same circulation patterns that concentrate natural organic matter also concentrate human debris, creating garbage patches where plastic and other non-biodegradable materials accumulate. The Great Pacific Garbage Patch, located in the center of the North Pacific Gyre, contains millions of tons of plastic debris. Contrary to popular imagery, this is not a solid island of garbage, but rather a diffuse area where plastic particles are more concentrated than in surrounding waters.
The plastic in these garbage patches exists mostly as small fragments suspended throughout the water column, much of it invisible to the naked eye, but detectable by scientific sampling. These microplastics can be ingested by marine life at all levels of the food web, from microscopic zooplankton to large fish and seabirds. The plastics can carry toxic chemicals and may cause physical harm to animals that mistake them for food. Ocean gyres also play crucial roles in marine ecosystems by transporting nutrients, heat, and marine life across vast distances. The Gulf Stream transports tropical species northward, occasionally bringing exotic fish and invertebrates to temperate waters. Similarly, the Kuroshio Current in the North Pacific carries warm water and tropical species northward along the coast of Asia. The boundaries of ocean gyres often coincide with major biogeographic boundaries where different marine communities meet. These transitional zones can be highly productive areas where upwelling brings nutrients to the surface and different water masses mix. Many commercially important fish species concentrate along these boundaries, making them important fishing areas. Climate change is beginning to affect ocean gyre circulation. Changes in wind patterns and ocean temperatures could alter the strength and position of these ancient circulation systems. Some climate models predict that gyres may intensify as wind patterns change, potentially affecting the distribution of marine life and the transport of heat around the globe. The stability of ocean gyres over geological time has allowed marine life to evolve complex life cycles that depend on current patterns. Many species of fish, sea turtles, and marine mammals have migration routes that follow gyre circulation patterns, using the current to reduce the energy cost of long-distance travel. Disruption of these circulation patterns could affect species that depend on them for reproduction and survival.
Satellite observations have revolutionized our understanding of ocean gyres by providing a global perspective on their variability and change. Satellites can track the movement of eddies within gyres, measure changes in current strength, and monitor how the gyres respond to climate variability, like El Niño and La Niña events. The gyres represent one of the most powerful and persistent features of our planet's circulation system, moving more water than all terrestrial rivers combined and shaping climate patterns that affect billions of people. Understanding how these massive circulation systems work and how they might change is crucial for predicting future climate and managing marine ecosystems in a changing world. As we reach the end of our journey through the ocean's hidden depths, we've traveled from the sunlit surface, where phytoplankton create the oxygen we breathe, to the crushing darkness of ocean trenches, where life thrives in conditions that challenge our understanding of what's possible. We've explored underwater mountains taller than Everest, forests of kelp that grow faster than any terrestrial plant, and ancient currents that carry the memory of past climates across thousands of kilometers. We've seen how the ocean creates its own weather systems that operate on timescales from days to decades, hosts alien ecosystems around hydrothermal vents powered by Earth's internal energy, and preserves our planet's climate history in layers of seafloor sediment that span millions of years. We've discovered that whale songs can travel across entire ocean basins, that microscopic organisms produce half the oxygen in our atmosphere, and that the deep sea contains more living space than all other habitats on Earth combined. We've learned about the ocean's role as a global circulation system that moderates Earth's climate, transporting heat from the equator to the poles and carbon from the atmosphere to the deep sea. We've explored how marine life has adapted to every niche in this vast environment, from bacteria that thrive in boiling hydrothermal vents to fish that survive crushing pressure in the deepest trenches. The ocean reminds us that our planet is more water than land, more unknown than known. Each fact we've explored represents years of scientific research, technological innovation, and human curiosity about the blue world that covers most of our planet. Yet for every question answered, the ocean poses new mysteries. New species are discovered regularly in its depths. New ecosystems are found in places once thought lifeless, and new connections are revealed between ocean processes and global climate. We've learned that the ocean is not separate from us, it is part of us. The water in our bodies has cycled through its depths over geological time. The oxygen we breathe was produced by its microscopic plants drifting in sunlit waters. The climate that shapes our weather comes from its currents and temperatures. The seafood that feeds billions of people depends on its productivity. Our future is intimately connected to the health of these vast waters. The ocean operates on timescales that dwarf human experience. Deep waters carry chemical messages from climates of centuries past. Corals and seamount communities grow for millennia, building reefs and ecosystems grain by grain over thousands of years. Ocean circulation patterns that determine our planet's climate operate on cycles that span thousands of years. Yet human activities are changing the ocean faster than it has changed in millions of years. As we face challenges like climate change, ocean acidification, and pollution, understanding the ocean becomes more critical than ever. The ocean's capacity to buffer climate change through heat and carbon absorption is enormous, but not unlimited. Its ability to provide food and resources for a growing human population depends on maintaining healthy ecosystems. Its role in regulating Earth's climate makes it central to our planet's future.
The ocean's mysteries continue to unfold as technology advances and our exploration capabilities improve. Autonomous underwater vehicles explore the deepest trenches, carrying cameras and sensors to places no human has ever been. Satellites track currents and marine life from space, providing a global perspective on ocean changes. Genetic sequencing reveals the incredible diversity of microbial life in seawater, showing us that most marine biodiversity remains invisible to traditional observation methods. Each new discovery adds to our understanding while revealing how much more there is to learn. Every expedition to the deep sea finds new species. Every analysis of seawater reveals new chemical processes. Every long-term study shows new patterns in ocean behavior. The ocean continues to surprise us, challenge our assumptions, and expand our understanding of life's possibilities. The ocean connects all life on Earth through currents of water, chemistry, and energy that span the globe. What happens in one part of the ocean affects all others, just as what happens to the ocean affects all life on land. The Amazon rainforest depends on dust blown from the Sahara Desert across the Atlantic Ocean. Arctic ice affects sea level and storm patterns around the world. Coral reefs protect coastlines from storm damage while supporting fisheries that feed millions of people. We are part of this connected system, dependent on its health for our survival and responsible for its protection. The choices we make about energy use, pollution, and resource consumption affect ocean health and, ultimately, our own future. Understanding these connections is crucial for making decisions that protect both marine ecosystems and human societies. As you drift towards sleep, imagine yourself floating weightlessly in warm tropical waters, sunlight filtering down through the clear blue depths in shafts of gold and green. Schools of colorful fish swim past in the distance, their scales catching the filtered sunlight like living jewels moving in perfect synchrony. Somewhere far below, in the eternal darkness where no human light has ever penetrated, bioluminescent creatures create their own constellations of blue and green light, communicating in flashes and glows that tell stories of survival and partnership in the deep. Ancient currents carry the stories of distant storms and faraway shores, mixing waters that have traveled from polar ice to tropical reefs and back again. The ocean holds you gently in its vast embrace, as it has held life for billions of years, supporting and sustaining the complex web of relationships that connects all living things. The ocean's rhythm becomes your rhythm, the pulse of currents that circle the globe, carrying heat and nutrients to every corner of the sea. The breathing of tides that rise and fall twice daily in response to celestial forces. The circulation that never rests, moving water and life in patterns that have persisted for millions of years. In its depths lie answers to questions we haven't yet learned to ask, and wonders we can barely imagine. The blue frontier stretches endlessly in all directions, patient and vast, holding secrets in its deepest trenches and mountains, in its ancient currents and seasonal cycles, in the countless organisms that call it home. From the smallest bacteria to the largest whales, from the brightest surface waters to the darkest abyssal plains, the ocean encompasses the full spectrum of life on Earth. The ocean awaits the next tide of discovery, the next generation of scientists and explorers
who will continue to unlock its mysteries with new technologies and fresh perspectives. Autonomous vehicles will dive deeper than ever before. New sensors will reveal chemical processes we never knew existed. Genetic techniques will catalog biodiversity we never knew was there. Each advance will answer old questions while revealing new ones, continuing the endless process of discovery that makes ocean science so captivating. In its vast embrace, past and future meet in the eternal present of waves and tides, currents and creatures, in the endless dance of life in the sea. The ocean carries the memory of our planet's past in its chemistry and sediments, while its responses to current changes will shape the future of our climate and our world. The ocean teaches us patience, showing us processes that operate on timescales far longer than human lives. It teaches us interconnection, demonstrating how local actions can have global consequences. It teaches us humility, revealing how much we still don't know about our own planet. And it teaches us wonder, showing us that our world still holds mysteries and beauty beyond our imagination. Sleep well and dream of endless blue horizons where science and wonder meet in the depths of the sea. Dream of worlds within worlds, of creatures that make their own light in eternal darkness, of mountains and valleys hidden beneath the waves. Dream of ancient waters carrying the memories of our planet's past and the seeds of its future. Dream of coral cities built by tiny animals over thousands of years, of whale songs that travel across continents, of currents that never rest in their circulation around the globe. Dream of life in forms we have yet to discover, in places we have yet to explore, in depths we have yet to fathom.
The ocean surrounds us, sustains us, and connects us to all life on Earth. It is our planet's greatest feature and our greatest mystery, our most important resource and our most challenging frontier. In its depths, we find not only scientific knowledge, but also perspective on our place in the vast system of life that covers our blue planet. Thank you for joining me on this journey through the ocean's hidden worlds, for exploring with me the science and wonder that lie beneath the waves. If you enjoyed drifting off to ocean science, please like and subscribe for more explorations of our planet's most amazing places. But for now, let the gentle rhythm of the waves carry you into peaceful dreams, supported by the vast blue embrace of our ocean planet. Good night, and may your dreams be filled with the endless wonders of the sea.